If we were able to find the true critical point of the brain, we will be able to model, to build a theory of the brain. So this allows you to simplify the problem and connect these theories and see the symmetries between these phenomena.
Hello, everyone, and welcome to another episode of In Plain English, the podcast that is all about making science approachable, open source, and jargon-free. I'm your host, Jamie Moffa, and today we are going to be talking about neuron connectivity and criticality, which, despite being a neuroscientist, I don't really know anything about. With our expert, Leandro Fosque. Leandro, can you introduce yourself?
Hi, I'm Leandro Fosque, and I come from a physics background, and I'm now a postdoc in neuroscience, a CTCM fellow at Washington University in St. Louis.
Awesome. Thanks for being with us today. And then our non-expert guests are Alejandro Gonzales Castillo and Peter Thatcher. Can you each introduce yourself?
Sure. I'm Alejandro Gonzales. I'm a PhD student at the University of Washington, St. Louis in economics. Fourth year, had the pleasure of being here. Before talking about the growth today, excited to be a non-expert and learn about the brain.
Yeah, absolutely. And Peter?
I'm Peter Thatcher. I'm a master's student at St. Louis University in Geographic Information Science. This is my first term.
Cool. So Leandro, take it away.
Yes. So let's talk about brain criticality. The concept of criticality came from physics, from the study of phase transitions. For example, what happens to a metal when you reduce the temperature such that you hit a particular temperature and suddenly you have a spontaneous magnetization in the metal. There is a point in which that happens. You go from non-magnetization to magnetization. There is a point right in between that is called the critical point. And at that point, what we see is clusters of spins, we call them, the little electrons pointing in a particular direction. If all the electrons point in the same direction, you have magnetization in one particular direction. But if you have clusters of spins of different sizes and pointing in different directions, that is what we observe at the critical point, right in between non-magnetization and magnetization. Now, how does this relate to the brain?
Let me interject right there, Leandro. So would it be accurate to say that this critical point is it similar to like what in mathematics you call a bifurcation point of dynamical systems? Is that it, or?
Yes, it is very similar. Not every bifurcation is a critical point, but a critical point is a bifurcation.
Gotcha. Great. Yeah, so I mean, just I guess to jump, I don't know if this helps anybody. So I took a math class, but a bifurcation is when you have a system that evolves through time, right? And you have a certain point that's of interest. And at that point, the properties of the system change drastically, right? So to give you an example, I mean, in economics, which is my field, you could have, the dynamics of unemployment, and there's a point where unemployment is stable. And then if something happens, if the economy changes slightly, it might be that unemployment starts fluctuating wildly or it disappears altogether. Mm-hmm. So bifurcation is like a generic, or this critical point is like a generic name for a point where a system has a qualitative change, in its properties. I don't know if that helps, Peter or, Jamie. I think that helped me understand it.
I was also thinking of like a more common, or at least like when I was taking like chemistry in high school, we learned about like a triple point where you have like solid, liquid, and gas at a certain like temperature and pressure. And that kind of seemed like what you were getting at with the like magnet, not a magnet.
Well, yes, but that is a perfect example, actually, because and that goes back to not every bifurcation is a critical point, because the critical point that I mean, you can have two main types of phase transitions, we can say. One where you go from one particular phase, the system is in a particular state, and you tune a parameter, I don't know, in the example of economics, but say you call it temperature or something like that, and suddenly you jump to another state. So now you were in state A, and now you jump to state B. And then you have others, which is there is a continuous transition. So one is discontinuous, you jump from one state to the other, and the other one is continuous. Now, in the continuous one, that is the one that shows you a critical point, because you need to have a point in between these two phases in which these two phases coexist. And that is where you start seeing this very complex behavior, and you start seeing what are called fractals, scale invariance. So this scale invariance is the signature of criticality, of critical phenomena, that you don't see in the other cases. Like, for example, when you were talking about the three critical point, where three phases, you can jump between the three phases, solid, liquid, and vapor. That is a sudden change. But you have another point, which is liquid to gas, where at that point they can coexist. And that is a critical point. No? And that gives you what is called critical opalescence, because you start seeing clusters of gas, of different radius and densities, and it scatters light at all wavelengths in principle. And you see something similar with magnets, spontaneous magnetization, and which is called ferromagnetism and paramagnetism. And right in between, you have the critical one. Now, how does this relate to the brain? You can think of the brain, say the neurons being in state 1 or 0. No, they are active or inactive. That's it. So now you activate a neuron, and that neuron activates its neighbors. But sometimes it may not activate them.
Well, it can also inhibit its neighbors.
It can inhibit too. And I'm not gonna get into that part because it's more complicated. But let's imagine that these are all excitatory neurons. What we observed in neural data, and this was in the 2003, we started seeing clusters of activity, spatiotemporal clusters of activity in the raster data. You have neurons in the y-axis and time in the x-axis, and you start seeing these clusters of activity bounded up by periods of silence, and then more bursts, silence, bursts, silence. When you grab all these neuronal avalanches, we call them, when you collect all these and you make a little histogram, and you plot them in log scale, and you say, okay, what is the size of this avalanche? Say you grab one of these clusters, and you look at how many activations there are, how many spikes there are in that cluster. Mm-hmm. That gives you the size of the avalanche. And the duration of the avalanche is the actual duration, in, say, milliseconds or whatever. If you grab, say, all the sizes of the avalanches that you see in the recording, and you plot them in log scale, you plot the probability distributions, you see a scale invariance, which means that you will find avalanches of size 1 and avalanches of size whatever, depending on the system size. It may be like 1,000 or tens of thousands or whatever. It will depend on the length of the recording and the size of the network. And the same we see with durations. So we start seeing these power laws, and people were wondering, okay, this is the signature of criticality. It is not enough, because I think in the 70s already, people were seeing power laws in everywhere: forest fires, earthquakes, rainfalls, avalanches, actual avalanches, and social dynamics and whatnot. But something that I didn't mention about criticality from physics is that these power laws give you, if you look at the slope of the power laws, that is called the critical exponent. If a system is truly critical, that exponent is unique to the system. And the exponents are related to each other by some, we call them a scaling relationship. It's an equation that has to be derived with particular mathematical tricks and whatnot. The fascinating thing is that if you look at this set of exponents, they for liquid to gas, and from magnetism going from paramagnetic, no magnetism, to ferromagnetic, that at that critical point, both belong to they have the same set of exponents, and we call them we call that a universality class. We say, okay, these belong to the universality class. So what does that tell you? Why is that?
You're going to have to, there's a lot here. Unpack this a little bit, okay. if you would be so kind, Leandro. So let's roll back a little bit, just because to make sure I understand all the terms that you're introducing. So people came, measured brain activity, right? And they found out that this clusters of neurons kind of activated, right? And so I don't understand, like, what does scale invariance mean? Does it mean that when these clusters were activated, they were not around a given magnitude? Sometimes they activated by a lot, sometimes they activated by a little. Is that what scale invariance means in this context, or?
The scale invariance is observed in the size and durations of these clusters. So you have a recording, say, of 1 hour, and you collect all these avalanches, and you see that there are a bunch of avalanches of size 1 and a bunch of avalanches of size 10 and so on. No? But you observe avalanches of all possible sizes.
Gotcha.
And all possible durations. So that is what we mean by this scale invariance. And if you bring it back to this fractality, it will be like you zoom in and you observe the same thing. You zoom in again and you observe the same thing. You zoom out, you observe the same thing.
All right. So there's another way of saying that there's no like empirical regularity on the size and duration of this thing. So it's all over the place, right? That's what scale invariance means. Okay.
It's not that you're going to find the average size of the whole system,
Right. Okay. And then if I understood your point about exponents, you're saying, okay, there's a scientist that knows a lot of math. And I want to study whatever, right? How pasta boils, right? And I want to study how like the bubbles around the water are. So I say, I have the suspicion that I can model this as a dynamical system, and there might be some, critical behavior here, right? So then the test of that is that I have to find this guy called the exponent, right? Which uniquely characterizes the behavior of the criticality. Is that correct? That's like empirically what we're looking for. Does that make sense?
Okay. Yes. So once you collect all these sizes of avalanches, say you make this histogram and whatnot, you get this probability distribution, and you see that they have one particular slope. That is your critical exponent.
Gotcha. And this is the slope of an histogram of what? Of like
it's a probability distribution where you say, okay, what is the probability of finding an avalanche of certain size? That is on your y-axis. Your x-axis is the avalanche size.
And that thing, so if it's equally as probable to find of any different sign, that slope has to be flat. Is that correct? Or
yeah. This is what they are called power laws, no?
Gotcha.
Because you can write it. You can write the probability distribution as a power law.
A Poe law.
Power law.
Power law. Oh, sorry.
Which is again that signature of critical phenomena.
All right. So then, what you said in this paper, if I understood correctly, you said, okay, we have a hunch that the brain and all these neurons, there's evidence that that we can think of this as a dynamical system, and like this. There's a critical point. But if that were true, we need to look for this guy, for the exponent defining its university class, right? But people haven't been able to find that guy, which would be like the empirical evidence we need that there's criticality. So you came in and said, okay, I found that guy. Is that an accurate?
Well, the thing is that people claimed to have found that guy, those experts.
They found the guy.
A while ago, but then more people started finding different guys.
Gotcha.
And then the community was like, okay, what is going on? Which are the true exponents, Because once you find the true, if the system is truly at the critical point, and this is the reason why we want to do all these tricks and whatnot, all this research, is because if we were able to find the true critical point of the brain, we will be able to model, to build a theory of the brain.
A mathematical theory of the brain.
A mathematical theory of the brain, yes. And as I was mentioning before, that we find that, okay, the magnetism, or ferromagnetism, at the critical point belongs in the same class. It has the same exponent, guys, as water transition from liquid to vapor. One model may be much harder than the others. So this allows you to simplify the problem. And connect these theories and see the symmetries between these phenomena.
Right. Like the brain is really complicated. There's a lot that goes into studying it, which, like, I know, being also a neuroscientist. But if the brain has this feature of criticality, and it's criticality, like, you find the same guy as an easier system to study, then you can study that system and generalize those findings to the brain and understand things about neuronal activation and, like, connectivity between neurons and, like, what different activate, like, you know, if you're sleeping, what might happen because the brain is in this kind of state, right? Like,
yeah.
Okay.
Yes.
Okay.
Yeah. And people claim to have found that class that is called the universality class of the brain. And funny that that class is called mean field directed percolation, which is basically the same or a similar universality class as the phenomena that you observe when you make coffee.
I was going to say, you said percolation. I'm like, is this going to be about, it is about coffee.
Yes, it is very similar to that.
So it turns out that this exponents, right? So they differ depending on, like, who you measure, right? The time of day and all that, right? So that's kind of the anomaly that you're trying to resolve, no?
Yeah. Yes, exactly. And what we claim is that critical phenomena, as we thought it in equilibrium systems and even many non-equilibrium systems, is that you have what is called separation of time scales. What is this? Let's think of a sand pile.
Like on the beach.
Yeah, you're on the beach and you want to make a sand pile, but 1 grain of sand at a time. So you drop grains of sand and boom, boom, boom. At some point, I don't know, it will take you a while, but at some point you start seeing a pile, and that pile has a slope such that when you start dropping more grains of sand, you start seeing these little avalanches, and accommodates a particular slope. So if you grab that model, you will see also when it reaches that slope, you will see avalanches of all sizes, and that is also a scale invariant. The question of criticality is a little bit trickier, but we see scale invariance. The trick is that you drop a grain of sand at the time. You drop a grain of sand, let it relax, let the avalanche finish, and then you drop another grain of sand. So if you think about the brain, it's like, okay, you activate this neuron, let the avalanche propagate, stops. When it stops, you activate another neuron, and so on. But that is not how the brain works. The brain gets activations everywhere, almost all the time. So that was the problem that we were trying to answer. If you want to talk about criticality, pure criticality, you have to talk about the separation of time scales. And we were saying, no, in reality, the brain doesn't work like that. It receives noise. It receives input from the external world, from other networks in the brain and whatnot. And that in itself will change the exponents. So if you were to go to separation of time scales, then you would find these real guys, the true universality class. But once you start adding these noises and you eliminate the separation of time scale, then you have many other exponents.
A whole bunch of guys.
Yeah.
So can you perhaps rolling back? I mean, I think I can understand what the research question and what you guys are doing, but going back to earlier to Jamie's point, so for those of us who are not, not in this field, but of course, I presume people have analyzed the brain and how the brain works for, at least 100 years, right? And there has not always been like mathematical theories to describe brain activity, right? So what is the promise of building a mathematical theory of brain activity and understanding how these neurons work? What sort of, current puzzles that we don't understand about how the brain works would it allow us to uncover?
Yes. So it would allow us to see how the brain self-organizes to reach this point. What are the benefits of being at this point, first of all? How does the brain self-organizes to reach that point too? And what happens when this principle is broken? What happens to a brain that is not acting near this critical point? So those are some of the most pressing and practical questions. The more theoretical questions is that it would allow you, it would constrain the theory that you are allowed to build for brain dynamics.
So, Jamie, I know that you're a neuroscientist, obviously, but as far as I understand, you don't work with any. I was surprised to learn as an economics, they have a fascination with math, but you don't do a lot of math on your research, right? You cut up rats and analyze their brains, right? So I wonder, based on like the research that what you're doing, I mean, do you see any possible benefits to what possible benefits do you see as someone who studies the brain in a non-mathematical way to, all of this stuff we have been discussing?
Yeah, I mean, so like one of the, like there's a relationship between experimental neuroscience and theoretical neuroscience where like people develop theories and then you can experimentally test those theories and then use the experiments to update the theoretical model, and you like kind of go back and forth. So like that's just one way that I've like seen these two branches of research come together. I kind of wanted to so I've heard a tiny bit about like criticality, because of course you have to take sort of like a survey neuroscience course at some point in your like neuroschooling, right? So there are people who do more of this research like in the big neuroscience building that I'm in, and I've talked to them, and like how they've kind of explained it to me, which I'm going to use to explain what I think the benefits are, is that like the potential for research is that why criticality is important for the brain is that like if you are in an instance where like some network in the brain is getting like too much input, like it's basically going to drown it out. Like if it's spiking all the time, there's no information. And also if it's spiking never, there's no information, right? If it's getting too little input, you don't get any benefit from that because like there's no information being transmitted. So like either way overdrive of neural networks or way underdrive is not going to be useful. But like that there's this sweet spot where you have like the perfect balance of like excitation and inhibition, the perfect balance of things that are pushing the network to chatter more, and the perfect balance of things that are saying like, hey, whoa, slow down. And it kind of can vary around that point to convey in the most like powerful way, like, hey, this thing is happening, right? That's like the very, very, very basic understanding that I have about like criticality in the brain, is that it's the point where you can get the most dynamic range out of the information that you're putting into a particular network. And I think that is important to understand for basically everything that the brain does, because the brain is, when you get down to it, a system for receiving information, processing that information, and then updating an organism's like behavior or views of the world in a way that's going to promote that organism like achieving its goals or surviving or like, well, whatever it is that it wants to do, right? So like in my field, I study pain. Very important to understand how information is transmitted for pain. And like experimental neuroscientists will study the like literal physical basics for how information is transmitted. Like you have the receptors in your skin, and those are located on nerves that send information to your spinal cord. And then that sort of gets bundled in this large information network that goes up to your brain and then like tells your brain that you're in pain. And then this modifies your behavior to make you be less in pain, right? But understanding like, I could see like uses for understanding criticality, because like that might also explain what's going wrong when someone has a like chronic pain condition, when they're just getting pain signals constantly all the time. And there's a physical problem there, but there's also like a central information problem there. And I could see like understanding a theory of big picture how information is scaled and how like the response of the brain is scaled to pain information being important for understanding like, can we modify that with like electrical stimulation, right? And what kinds of electrical stimulation can we use to modify how the brain is processing all this information that's coming in?
I think that was a better explanation. Yeah, because I didn't get to the whole branching process and information transmission, which are the benefits of criticality that people have been arguing for almost 2 decades now. Is that, well, actually much before the experimental evidence. It can maximize information transmission. It can maximize dynamic range. It is more susceptible to the information that is going to be perturbations in the network and whatnot. So yes, it has a lot of benefits for computation. So a network that operates near the critical point, it optimizes computation. The other thing that people are exploring, like for example, where I'm working now in Hengen Lab, they are looking at sleep. What happens during sleep? If during waking experience, this criticality measure starts degrading. And when you go to sleep, it gets recovered. Another case is epilepsy, where you jump into a completely different phase when you have an epileptic seizure. What happens to these networks? Why are they so susceptible to jump to those phases, epileptic seizures? And another work that has been done at my lab, at Hengen Lab, at WashU, is Alzheimer's disease. Accumulation of tau, for example, and how that affects the network and this criticality measure too.
So I have a question about sleep. I guess because I'd heard that theory generally about sleep and criticality. Is the theoretical basis that like sleep is kind of a recalibration because it's closer to a state of sort of zero-ish inputs than like when we're walking around constantly receiving visual input, constantly receiving sensory input, that like when you're asleep, the neural networks can sort of recalibrate and be like, okay, this is kind of where we want to be, instead of like constantly drifting because of inputs that are coming in.
Yes, it seems to be that there is a rescaling of the network that avoids that drifting that happens during waking experience. And these results are pretty recent. It's still being debated what is really going on, but the data seems to point in that direction. The mechanisms that bring the network to this optimal regime during sleep, that is still not understood. That is exactly what I'm working on right now. And also to see what are the benefits of this mechanism for potentially any computational system in general. Forget about biology for a moment and think of a neural network, an artificial neural network that is able to compute efficiently. What are the benefits of being near this critical regime for the network?
Let me go. I mean, feel free to shoot this down, but let me go completely sci-fi for a minute. So, I mean, obviously, the hot topic of the day is AI, right? It seems everybody's talking about AI. And for those of our listeners that don't know, not that I'm an expert on this, I know a little bit about this, but in some ways, our models of intelligence, or that when we program things to do things, are much more stylized than what our actually cognitive processes are, right? I mean, I imagine because they're very algorithmic call, right? Like do this, if not do this. I imagine it looks nothing like the complex dynamical system that our brain is, right? Which of course Leandro studies. And in other ways, it's much more sophisticated than us, just because they have raw computational power that we don't have, right? So an obvious example of this is chess, which is almost close to being solved. Like you just compute all possible moves, and now you can almost figure out a draw, which would be impossible just because you can visualize and imagine how all the places move in a board, right?
Even Go,
even Go, right, even Go. So here's, I guess, the sci-fi part. So we have these models of how to try to with these neural networks and machine learnings, which are very crude in some sense approximations of what we do. And we have what you're doing, right? Which is like this mathematical theory of how the brain works. Do you envision at some point a convergence of these two approaches where we can either, I guess, use our more sophisticated model of the brain to improve drastically, right, this AI and like the decisions they make by using some of the insights that we have from how the brain actually works? Or conversely, do you think that we'll ever be able to, like, I guess, I don't know, full cyborg here, but like integrate some of the stuff that AI does into our brains through the understanding of the mathematical properties? I mean, feel free to shoot me down. I'm just curious on this.
That is a fascinating question, and it's a super hot topic now. We just had the Neuro AI Symposium here at WashU, and these are popping up everywhere now throughout the world. First of all, AI is highly inefficient. It's terrible at the state it is now. We use very little power, and we are able to be much more flexible than neural networks nowadays, to the point that now Microsoft has to buy an entire nuclear reactor to feed its own AI. It is highly inefficient, and that is one of the main problems that we have nowadays, is how to make this. I don't know if it will be in terms of the algorithm, in terms of the software, or it will be in terms of the hardware, because our information is stored in the structure of the network. The memories and all that is stored in the structure. And how can we do that with a hardware, for example? That is one of the questions of today. The other thing is that they are very bad in terms of flexibility, the current algorithms. You teach a task, yes, they are great at playing chess, but and maybe the best, not playing chess, but you add a little bit of noise, or you try to teach it how to play Go and how to interpret a novel or something like that, and it won't be able to do it. It's extremely hard to reach that flexibility. So that is on the side of neural networks. The other thing, most neural networks, they operate to what is called firing rate models. And teaching networks to operate under spiking mechanisms like the real brain, it is much harder. They are very prone to break if you add a little bit of noise. So it is. We are still, I think, in a pretty young stage with respect to AI. Now, the benefits from AI to understanding the brain, there are many, but I don't know. Me personally, I don't know how to feel about that, because there is this thing that we don't understand and this other thing that we don't understand. So we have two things that we don't understand and we want to explain one with the other. Like, I don't think we will be able to make much progress with that, but we will be able to predict nice things. And this is a current problem with machine learning too. It is very nice. You feed this data to a machine learning algorithm and it's able to predict whatever, some time series. But it's a black box. It's not telling you something about what is the real model that is giving you the dynamics. You may be able to predict some things, but at that point it becomes, you cannot build a theory from that. And that is a problem that we are seeing more and more in science, that people are driven towards machine learning algorithms and whatnot because they want to feed data and they want to be able to predict very quickly. But to me, the most interesting question is trying to understand what is going on.
That actually feeds into, I believe this episode will come out before the episode I'm talking about will come out before this current episode. But I just recorded an episode on a sort of dimensionality reduction algorithm called UMAP. And that was kind of the main problem that we arrived at with UMAP, is because it uses machine learning to basically take super high dimensional data where there's thousands and thousands of different parameters by which this data might vary, and smush it down into 2 dimensions so you can put it on a page, and you can fiddle around with some of the parameters like when you're making your graph, but you don't know, other than that, how precisely the algorithm is taking your points and turning them into a nice pretty colorful graph on the page. So yeah, there's not really much, and the conclusion we came to is like there's not really much like statistics or hard concrete science you can do with UMAP. It's just a pretty representation of some features of your data and what it might look like.
So I guess one of the possible responses were like, okay, if we were managed to figure out how to, let's say, open up Peter's brain, right, and put like a machine there that allowed Peter like to, to play chess the way like Stockfish plays, right, with like this huge computational capabilities, it would require so much power that it would be unfeasible, right? Or like we would have to plug Peter itself to like a nuclear reactor to make this work, right? So
there's that. And there's also that's one of the problems. The other problem is like the existing network of your brain is so complex that where would you basically how would you connect it to how would you integrate that with the existing brain to be able to seamlessly integrate information from this like computer chip with the information in your brain? Like, the order of complexity, even of like really, really basic quote unquote processes, is such that like, cochlear implants, you put a thing and there's electrodes that connect to nerves in the inner ear that allow for auditory stimuli to be transmitted in the absence of functional biological nerves. And this can assist people who are deaf or hard of hearing. That is one of the most quote unquote basic systems in the human nervous system, because there's this set of nerves that conducts acoustic stimuli, transmits them into electrical information, and sends them to a particular part of the brain where they are processed. And it's still not very good. Cochlear implants are not hearing in the way that we all understand hearing. It's when you hear people describe cochlear implants who have them, it's a totally different experience. And we can only barely recapitulate that. We can't do it with vision. Like, you can't help someone who is blind for neurological reasons see with a similar implant, because vision is an even more complex processing pathway. But even that is less complex than understanding how to play chess. So I guess my point is like, how would you even integrate that into the brain's existing network?
No, but that's fascinating. Thank you. Great experts.
Yeah, no.
But the conclusion is fascinating work, but we're very, very far away from using any of this mathematical findings to either help us integrate with either Neuralinks or with like to inform the other research agenda of like how AI things, right? Do I read you correctly?
Well, there are people that have tried to connect criticality with machine learning. There was a recent paper, I don't remember the authors, but big names, in artificial intelligence, that try to show that yes, criticality is setting up the network to criticality is beneficial for feed-forward networks, and I think it has been shown in recurrent networks too, but that's it. That is pretty much the extent to where it goes. But in terms of health benefits, yes, we have been able to connect it. Still is pretty new, the applications that we are bringing to I wouldn't say the clinical work per se, but to understanding what happens if you break with this criticality measure. That being said, even though we are using the word criticality constantly, what we were trying to show in this 2021 work is that the networks are not really critical. The networks are quasi-critical. They are near the critical point, but because of different parameters that you change, maybe the coupling between the synapses, the strength of the synapses changes. If you make them super weak, information is not transmitted. If you make them super strong, it overwhelms the network altogether. So you have that parameter. For example, you have other parameters, the level of external drive and many other adaptive mechanisms that are not included in the model in this theory, but they are there and need to be investigated. So the measure that we usually use to say, okay, how close to critical it is and how far from it is, for connecting it to, say, sleep or Alzheimer's or epileptic seizures and things like that, is the measure of the relationship between these exponents that we obtain. That is, we call it the DCC, or distance from criticality coefficient. And that is the measure that we usually use, because as long as that relationship is held together, the exponents may change, but as long as that relationship is held together, then you are close to the critical point, or moving along this so-called scaling line where all these exponents coexist. Yeah, that is the main measure that we use for studying if that measure is if that equality is not sustained, if it breaks, that means that you're getting farther away from criticality and you start seeing problems in the network.
But so you already said, like, the brain is not at criticality. It's quasi-critical. I guess I don't know if this question makes sense because I don't know what like physical basis it would be in, but like how much tolerance does the brain have around criticality? Is it like a pretty wide tolerance? Is it still pretty narrow, even though it's not really critical? Or like, can you not even answer this question because it doesn't make much sense?
No. That is a great question, actually. The problem is that it is very hard to answer. We don't know. In the case of this paper that we're looking at, we didn't explore those limits. Where does it break? How much noise can you put in the network such that it pushes it away from this scaling relation? We don't know. And also, there are no adaptive mechanisms in this model. And now I'm working on trying to implement those adaptive mechanisms, because you drive the network and the network will respond in a particular way. It will say, no, okay, I need to fix these synaptic weights so I can get closer to the critical point. No? So there will be some self-adaptation. Well, maybe that is a redundant term. There will be some adaptation in which the network will try to come down to some homeostatic state.
I mean, because that's sort of a on the physical level, that's kind of a fundamental property of the brain at like all levels, from a neuron to looking at the entire brain, right? Is that it does have feedback mechanisms. So on the level of a neuron, I do a lot of electrophysiology where like you record from single neurons in either a slice or a culture of neurons. And there are some neurons that it doesn't matter how much current you put into them, like how excited you make them, they will fire a couple of times and then stop. Even though they're still like supposed to be in a really excited state, they're just like, nope. And it has mechanisms to stop information transfer. The same thing happens at the level of circuits. So an example that a lot of people might know about is tolerance for drugs like opioids. When you take opioid medications, that's putting into the system a level of like input into opioid receptors that your brain cells already have on them that is above and beyond anything your brain would ever be able to produce. And your circuits in your brain recognize this. They're like, this is way too much input. And they scale down the amount of receptors for opioids on their surface so that you are less sensitive to them as you take more of them, which is, a problem for pain science, but is a good example of how the brain has these feedback mechanisms to make sure that it's not just going completely overboard.
Yes, that is a great example. And honestly, here is where I think biology has a lot to teach to physics, because in physics, you go through your PhD and everything, and I would say almost nobody really explores adaptation. You're given an equation that describes the dynamics of the system, and you just run it and you see where it's going to be, what the different phases are and what not. But something characteristics of biology is that you have all these adaptive mechanisms. You have the threshold adaptation of single cells. You have the adaptation of the synapses, neuromodulators, and lots of feedback loops that are in a way trying to correct for certain errors that are accumulating in the network. And I think, yes, that physics doesn't have a way of studying that.
Peter, I feel like this has been a lot of me and Leandro like gabbing back and forth. What are your thoughts so far?
Yeah, I mean, it's definitely I think very new concept. Like I'm not really familiar, had never heard of criticality before I attempted to read these papers today. And I think I kind of understood it sort of when we were talking about bifurcation and then like it's sort of like moving and like this sort of idea of quasi-criticality. I think that would sort of make sense in relation. But yeah, I mean, I'm kind of curious of like what you would say like the basic definition of criticality is.
No, because I've been trying to formalize it a little bit better for dynamical systems people, because physicists, sometimes we tend to hand wave or definitions. Criticality is the phenomena that you observe in many systems in nature that exhibit scale invariance, this fractality that we were talking about.
Okay.
But that is a necessary condition, but not sufficient. So there has to be this relationship between the exponent guys that we're talking about. If you don't have that relationship, then you may be observing scale invariance, yes, but it may not be critical per se.
Okay.
And it is a little bit tricky because it was intended to be formalized. I think it was, I should know this, 70s, 80s, with something that is called the renormalization group. But the idea was that people were trying to formalize it much better mathematically. The thing is that applied only for a type of systems, systems that were in equilibrium. Some people tried to apply it to systems that were a little bit out of equilibrium. But it hasn't been completely formalized in a general way. And remember, the brain is highly non-equilibrium. So many of the things that we talk in terms of equilibrium doesn't work very well, or they are very vague approximations.
Definitely, yeah. And I guess like one other thing I'm kind of curious about, this is also sort of going to basics maybe, but it's sort of like, what it looks like to gather this information about people's brains. And like, so I think we're kind of at the very like theoretical mathematical level, but like, what does this kind of like look like getting this info? How long does this process take? Like, how long did you spend on this research to publish this paper? Some questions, about that. Curious about.
Yeah. So, well, in this paper in particular, it was with organoid cultures. So you take slices of brains and of rats in this case, and you cultivate them for a while, and then you do recordings. You have electro arrays, microelectro arrays, and you measure the activity, the extracellular activations, and then you collect these avalanches from the neural activity. But you can also do it with EEG data. You can do it with MEG data even. We have been able to implement it in those cases too in humans. We have been able to implement it in vivo. A lot of people have implemented it in vivo recordings. And yeah, all type of neural recordings we have been able to one of the important conditions is that you have to have quite a large number of neurons. You cannot do it with just one neuron or two.
So I guess for like implementing it for EEG, because you can't get activity of individual neurons, you're getting broad scale electrical activity across the cortex. Is the unit you're working with just larger? So like avalanches of cortical activity rather than avalanches of neuron spiking?
Yeah. So in the case of EEG, it will be what is called mean field in physics, because it's a collection, an average, basically, of a bunch of neurons. So in that case, how you they find the avalanche is a little bit different. You have this curve, and you take the area under the curve, and that will be the size of the avalanche, and the duration will be just 2 points. But it has been shown to be also scaling variant and satisfying scaling relation.
Does anyone, or does this theory even apply? Because all of this is like about the cortex, right? About that layer of the brain that's like sort of around the outside. It's a lot of cognitive processing, sensory processing. Has anyone applied this to subcortical areas? So like thalamus or brainstem, or like,
I mean, I have applied it to hippocampus, for example. Funny, because I was actually working now today on the thalamus, trying to apply that to the thalamus. So I don't know yet. We'll know soon. But no, people have applied it to different subcortical areas too. There was one region that didn't exhibit scaling variance for some reason. I don't remember which one was it, and if it was something consistent or it was just at a particular moment. Because something important too is that you don't see the scaling variance when the animal is performing a task during the task. No, performing a repetitive task, you don't see that. And I think that was in the motor cortex. It may have been in the motor cortex. So you have to be careful about those things too.
Why don't you see it during a task?
Well, because you're receiving a structure activity, no? And you are repeating those patterns in a structured way. If you measure from other regions of the brain, you will probably see scaling variance. But in the network or subnetwork that is performing the task and processing that information at that very moment, people argue that they haven't seen it in those cases. The other thing is that even though we are formalizing this with respect to the brain dynamics and whatnot, these theories also apply to many other systems, complex adaptive systems in general. Not obviously to every complex adaptive system, but to a large set of them. And it remains an open question. What is the true mechanism of that we observe in many phenomena in nature, going from forest fires to earthquakes to some critical phenomena in social dynamics and many other phenomena. That is still an open question.
Earthquake seems like an interesting one because it seems like a situation where you're doing more of that jumping states, right? Like you're at like a stable state, and then suddenly like the pressure builds so that you jump to an unstable state.
Yeah, and that is why now people are calling it intermittent dynamics. No? And even what you see in the brain, the avalanches, is in a way intermittent dynamics. So there is a stress being accumulated in an earthquake, no? And it reaches a certain threshold, and that stress needs to be released. Now, how it is released, that earthquake, the size of the earthquake, that is a scaling variant. If you grab the earthquake events, you will see that they are a scaling variant. So large events, very large earthquakes, they are very rare. Small earthquakes are very, very common. So that is what we observe. But that mechanism of accumulating this stress and then having to release it, that is what we call intermittent dynamics. And that, in a way, is what you see also in neurons.
Yeah, like they accumulate small inputs that push it either closer to a threshold or further away from it. And then if it reaches that threshold, then you see the activity. I can see that. Okay. Such a cool theory that it applies to everything from like little cells to social dynamics to like tectonic plates.
Something that is interesting, though, to get on a tangent, I guess, there. So, I mean, when I started studying economics, I wanted to apply these ideas of like bifurcations and, critical points and so on to study economic, phenomena. And it seems at first sight like intuitive because, I don't know, you see stuff like this great, the great financial crisis, right? Doesn't that represent something like there's something that changed, maybe bad macroeconomic policy or some financial system, and that, put you in a big recession. And a lot of economists kind of worked on trying to, in the 80s, on trying to incorporate many of these ideas into economics, and it was fashionable for a little bit, and it seemed like there was some promise. But then at the end of the 80s, what people found is that when you take like a lot of this dynamical systems are like super, super complex, right? And it turned out that they didn't, even though they were able to like qualitatively explain some phenomenon, they fitted the data really, really bad compared to much simpler models. Just like examples of like linear dynamical systems, which I think is it's just like a system of linear equations. Everybody learns that in high school. So you'll say, oh, what's a recession? You get hit with a bad shock, with a bad, I don't know, people spend less for some reason, right? And that was much, much simpler, and it fitted the data better, although in some sense the explanation was less rich, if you want, than a lot of these more complex dynamical systems. So I took a class on this, and I wanted to write my dissertation on this, and some people heard what you worked on that in the 80s, and they all told me this is dead. Like everybody abandoned this, and like nobody kind of thinks that this is useful anymore. So I mean, obviously not to what's the American expression, not to poop on the party of James that can apply to everything, but I think that there were some attempts, at least in social sciences, to bring these tools, and I still think that they may have some promise, but it just seems like sometimes the more complex theories don't describe the data better as our more simpler intuitions. But who knows? Maybe that changes. It could be cool to see that change.
Yeah, I'm not familiar with with economics much, but I've seen that the stock market shows certain fractality too. I don't know how that is mapped to some scale invariant behavior in terms of criticality per se, and also. Are the crashes, and I think we are going in a tangent now, but are the crashes scale invariant? Do you see a bunch of mini crashes and then big crashes that are more rare? A lot of mini crashes happening also.
That's a great question. So I think that for most of the developed country, you see recessions being mild, and you see, I mean, when recessions are big, they usually receive names, right? So you have the Great Depression, obviously, and the Great Financial Crisis, which were so there's a committee in the United States, the National Bureau of Economic Research, which is it a government? I think it's a government agency. Yeah, it is. So they have this very cool picture of you go like recessions in the United States, pops up. You see the unemployment rate, and since the 19th century, there have been like 16 or 17 recessions, and they have mostly been very mild, except for these two big ones, right? So I think that's why some people think that the idea that a lot of aggregate macroeconomic series are normally distributed is not like such a bad. I mean, first, if you go run test this, like kind of you'll reject, but there's not such a terrible first approximation. You see only occasionally this very large negative events. Now in the developing world, that's another story, right? But the problem there is that you have way less data, obviously, and you have less. The quality of the data is worse too. But yeah, if you think about the developed world or the world economy, which is developed countries weight more in that total GDP, certainly most recessions are mild, and there's only a few events which are very very. Now, the stock market is a completely different story, but we're talking about real things, right? Real tangible.
Yes. But the thing that I was wondering, and maybe it's completely off base or whatever, which is you have a central control, which says the government in the case of economics, and it accumulates certain error too, and then it needs to impose through some mechanism, a correction on the market. And you also have the other mechanism, which is people in themselves operating in a particular way, buying or not buying certain stuff, working or not working. And that is another correcting mechanism. And so there is one that is an integrated mechanism of error correction, and the other one that is more diffuse. And in the brain, we have similarities in that sense, no? That you may have EI balance, inhibition and excitation, that inhibitory cells start trying to quiet down excitatory cells if they get too noisy, or the adaptive threshold in the neurons, the individual neurons, also tries to correct for a lot of activations. But you also have integration of errors in the brain as a whole, in terms of neuromodulators, and even, and this is a hypothesis, even in the transition from wake to sleep. What is that drives you to sleep? Forget about the circadian rhythm, but talking about the homeostatic process, that you are reading a book, or you're working on hard problems for a few hours and you get super tired and you need to take a nap. What is that? What is that mechanism that needs to push you to sleep in that case? It seems to be something that is more centralized in the case versus the other one that is more diffuse. It's completely hypothetical.
No, it's an interesting idea. I guess the only thing I have to say is, which is, I don't know, of course it is very off topic, but perhaps surprisingly for the people hearing, is that there's not a lot of course, it's a personal judgment based on my experience on economics, blah, blah. So people are free to disagree. But when we study the most dysfunctional or interesting aspects, which I think you're alluding to, Leandro, right? Like recessions or crashes or like hyperinflations or periods with high employment, which is the domain of macroeconomics. That's what I do. You'd be surprised that most of the models up until, I don't know, 6-7 years ago, all shy away from the idea that there's, kind of a decentralized market where like people interact. They all operate under what's called the assumption of a representative agent. So it's the idea that the whole economy is as if a single person took all the decisions in the market, right? Mm-hmm. Which kind of sounds bonkers when you put it that way.
Yeah.
And there's some like results that say, well, if people are not that different, then it's as one person taking decisions for everybody is the same as everybody taking decisions. But we know that people are very different. I'll just put it that way. So these theorems are like of limited interest. But then I guess the other thing, which is the more, I don't know, like honest response, is that because it's very, very difficult to solve models or treat, models where you have like many, many agents that are doing different things and have like different that are different and have different wealth and even perhaps objectives. They very rapidly turn into a black box. Sometimes you can solve them numerically, sometimes you can't, but they turn into a black box. Like nobody really understands what's going on. And sometimes we come back to what I said earlier. It's not so clear that they fit the data better or that they help us, understand. So I think it's very surprising, but I think my colleagues, which are microeconomists, which are the guys that study just the allocation of, why are apples more expensive than pears? I mean, they answer more interesting questions than that. But that's kind of the kind of stuff that they study. They take much more seriously, the idea that there's different agents that interact in a decentralized kind of way. But for the more macro phenomena, I think we're still far away from like taking that seriously. But who knows? Maybe somebody says like, oh, we could model this like the brain and it'll be a huge breakthrough. But yeah, that's what I'll say.
That's an interesting point, because that brings back to this problem that we're talking about, modeling the brain. In physics, you have two main ways of formulating a problem that has a bunch of agents. You have what is called the many body, and you have the mean field. And the mean field will be take the average, consider everybody behaving the same, That's it. It simplifies the problem. And the other one is, no, you have to consider all of them, how they're interacting. It's very complex and whatnot. And the thing is that both will give you different exponents. So they will belong to different universality classes. So that is one of the main issues of wanting to go in one direction versus the other. Both are useful. But if you want to be super precise, you have to go to the many body or agent-based modeling.
So neuroscience hasn't figured out that problem either.
Modeling stuff is hard, is the conclusion. It's very hard. And it's very hard to do it in a way with that people actually understand the key mechanisms and what's going on, right? Without turning it very quickly into a black box, I feel like.
Yeah, and I guess social dynamics is way more complex because the degrees of freedom, the variables that you have to consider that are relevant versus the ones that are irrelevant, they're very hard to distinguish. Versus in a neuron, you have a limited number of options. If you go again to a metal, you have a way more limited number of options. The electron, say, particular models, it can be pointing in one direction or the opposite, and that's it. No more. So those are your degrees of freedom. In the case of social dynamics, it becomes more complicated.
I just kind of wanted to end with like everyone talking a little bit about like a cool or interesting takeaway, because like I certainly came into this being like, I don't really know what's going on. And I think this has been a really cool discussion with a lot of parallels to a lot of different things that interests all of us. So personally, I thought it was an interesting takeaway to be like to the question that got me thinking about, how could understanding criticality or quasi-criticality apply to answering biological questions about the brain? I was like, that was a really cool sort of thought process to go through.
This stuff is all very new to me, like, so I think I was, it's interesting that you're working towards a mathematical model of the brain, because that seems like a really, be a very big accomplishment for the world. So it's cool trying to take steps in that direction.
Yeah. I think my takeaway, which goes to the earlier discussion, I mean, seeing, because, I also understood not a lot of what was going on the papers, but I think based on our like discussions and so on, the idea that it seems to be that our neurons, right, on the brain, the math behind it or the way it works is like so fundamentally different from the way that people model decision making, not only in economics but just like how people say like, oh, we're going to try to build this AI or simple algorithms that like mimic decision making. It's like so radically different. Was very insightful to me. So it, I think it cements this idea that I know this is not fashionable to say in 2024, but humans are truly wonderful, and our brains are wonderful as well in the way we kind of work. So builds my fascination, my humanism, my fascination for the human race.
Oh, so optimistic.
Yeah, that those are very kind words. I wouldn't say wonderful per se, but interesting. Very interesting in the human beings, how we operate. But yeah, thank you. And this was fascinating. It helped me also to explain things a bit more careful. I don't know if I did a good job at that.
You did a great job. I understood
much better.
Nothing. I understood nothing from the papers. I was texting with Peter like, what are we even reading, man? This is a good shit. And then you came in and I think laid it out very clearly. I mean, at least for me, I think that having a background in math definitely, like, not that I have a degree in math, but having taken some math classes and knowing that dynamical systems kind of like helped quite a bit. But I think you did a great job. So
it may show how, I don't know, I tend to go on tangents. That is why I was in physics. My undergrad was in astrophysics. Then I did a PhD in physics, and now I'm doing neuroscience, working on neuroscience. So I tend to go multiple directions. So I try to think these type of problems in a more general way. That is why I like to think it also how it applies to social dynamics, how it applies. It doesn't mean that I'm trying to find one answer that answers everything, I'm saying that it is a very useful way of thinking about different problems, but that doesn't mean that it answers every single problem.
Right. And I think that's really cool to be able to go between different fields and then bring people like you who do that, bring critical knowledge from one field to another. And like, we like neuroscientists would kind of be stuck if we didn't have anyone that understands math and physics. This has been amazing. And thank you all for giving an hour and a half of your time on a Saturday to talk about complicated brain networks. This has been fantastic. And we have been talking loosely about the paper Evidence for Quasi-Critical Brain Dynamics by Leandro Fosque et al. With the first author himself, Leandro Fosque, and our two non-expert guests, Alejandro Gonzales and Peter Thatcher. You can find the paper on our website at inplainenglishpod.org. While you're there, check out the Continue the Conversation tab to send in questions or suggestions for future episodes. If you would like to be a guest on the podcast, either as an expert or a non-expert, you can contact us at inplainenglishpod@gmail.com. You can also follow us on Twitter, Blue Sky, Facebook, and Instagram at Plain English Sci. That's PLAINENGLISHSCI. Our music is by Sam Brunwasser. You can find more of his music at soundcloud.com/visualsnowbeats. The logo is by the wonderful team at Biographics. That's Tania Lintz, Yolanda Campos, and Jessica Higginbotham. Thanks for listening, and tune in next time for another episode of In Plain English.